let's look at three pretty neat examples related to pressure and in static fluids. So here's the first one. So assume that mercury, which is relatively dense, especially in comparison to, for instance, water, it's almost 14 times as dense, is inside the manometer, okay, so that you see there in figure 2. Now assume that the atmospheric pressure is 1 atmosphere, all right? If during a blood pressure reading, the manometer provides a systolic reading of 115 millimeters of mercury, then, all right, and it gives us a couple of things to answer. So first, what height did the mercury rise? All right, so that's the first thing. Blood pressure, okay, so whenever we have a reading of 115 millimeters of mercury, so that's the gauge pressure, right? So that's going to be above the atmospheric pressure, okay, that we have. So now if we want to know what the height is, okay, so we have to do the following. So first of all, you kind of have to recall and understand that pressure within fluids at the same depths, okay, is identical. So that means the pressure over here and the pressure over here, okay, they are equivalent. Now, once you know that, then it's relatively actually simple in order to figure this out. So let us get started. Okay, so the first thing that I'll do is, I will call this, let's say, pressure P1, and then this pressure P2. So what I have is pressure P1 is equal to pressure P2, okay, in a static fluid. And therefore, okay, so what I'm going to have is, well, for pressure P1, I can see there that I have the atmospheric pressure plus, okay, it's going to be the actual pressure coming from the fluid, in this case the mercury, okay, relative to this height that I have. So what I would have in here is I would have that this particular, okay, amount is nothing else but simply the density times the gravity, okay, times the height. And that is going to be equal to whatever pressure I have on the other side, which is PA. All right, so that's the pressure coming in, okay, and that would be the pressure, okay, which is coming in from the blood itself. All right, so that means that would have been the absolute pressure, okay, on that side. So if you are going to be doing this and you recall, okay, so when you have a manometer, okay, and you want to have the gauge pressure, really this is the only thing that we care about. So I'm going to just take this out because this is indeed the gauge pressure, right? So the rest, okay, kind of just follows through. So if this is the gauge pressure and it is equal to, in this case, 115 millimeters of mercury. Now I'm going to change this, okay, so let's just change it back. Okay, so that 1 millimeter of mercury, and it gave us, okay, which is 133.322 pascals. That's what they want us to use in the question. So I'm going to just remove this just so that it's all in metric standard units. And then now notice the density, okay, that I have, which is also given in the question. So here's my density right there. So which is 13.6. Okay, so I'm going to write this in here. So 13.6. Actually, I'm going to change it back. Okay, so let's remove the scientific notation. So times gravity, okay, and then times the height, okay, the mercury would actually rise. So notice the H is really the only thing that I have remaining. So if I'm going to calculate this through, okay, I'm going to do 115 multiplied by 133.322. That gives me what the pressure is in pascals. All right, so this is what I would have, okay, in here. And now I can take that pressure, as I have it on the calculator, and then I'm going to divide it, okay, and I'll divide it by these two, right? So this is divided by this whole thing, which is 13600 multiplied by 9.8, and it gives us, okay, what the height would be. So that H is 0.115, all right, meters, okay, or simply 11.5 centimeters, and that would have been the height in here. Now, in terms of rounding, I'm just kind of peeking through. I guess I'll just keep it to 3 significant figures, okay, so as it is. So there you have it. That's what you would have had for part A. So it wouldn't be really, a lot of distance, okay? I mean, 11 centimeters. I mean, it's still going to be a relatively, okay, distance, which would be pretty big. Now, that would have been in this manometer. Now, in part B, it says, with the given height, okay, so from part A, compute the gauge pressure, okay, in pascals. Then, using the conversion, check if the reading indeed is 115 millimeters of mercury. All right, so, well, the gauge pressure, as I said, is nothing else but simply this. All right, so this is what this would be. So I'm going to just duplicate this for part B. Let's duplicate that in, and maybe I'll change the color, okay, so that it just stands out for us. So that would have been the gauge pressure that I have. Now, if I take this, so 13600 multiplied by, and so within here, so this would have been 0.115 multiplied by 9.8, okay, so which is the height. So I think I still have this on the calculator there. So that's my answer in terms of the height. So let's take that and multiply it by 9.8 and then multiply it by the density of mercury. Okay, so notice that we're going to get 15332.03 pascals, right? And now, okay, so with regards to this, as you're going back, okay, so we're kind of going back in reverse. And so for this part number B, then we could now change this back in, okay, and use the conversion that 1 millimeter of mercury, okay, is equal to 133.322 pascals. Okay, so it's kind of going back in reverse and then just checking our answer. So within here, if you wanted to do that, you would have to take your answer divided by 133.322, and then you're going to get, which is your 115 millimeters of mercury, which was your blood pressure reading. All right, so that's what you would have done for this example. This is parts A and parts B. It's a nice little exercise to kind of get you understanding how the manometer is utilized within, or at least was utilized, okay, when it originally started. Now we use different tools, okay, in order to measure these blood pressure readings. All right, so that's the first example. Here's example number 2, okay, for this particular video. So it says calculate the buoyant force that would be present on an object that has dimensions of 12 by 18 by 30 centimeters, and it is fully submerged. All right, and it gives us all of these different densities. Okay, so let's start with A. So here's water first. Okay, so water, which has a density really of 1,000 kilograms, okay, per meter cubed. Okay, so that's this one right here. Now, if you want to find the buoyant force, well, really what we have, so I'm going to just kind of sketch this out in here. So if you submerge something, and in this case the volume, okay, so for us, so 0.12 times 0.18, times 0.30, so just change this back into meter. So if we know the volume of this, and you want to find what the buoyant force is, so the buoyant force is equal to the weight of the liquid that this would displace, right? So this actually comes back to Archimedes' principle. So if that is equal to the weight which would have been displaced, well, weight is just mass times gravity, all right? Now gravity we have, and this is where we're gonna need the density, because density is equal to mass over volume. So we can get what the mass is by simply taking the density and then multiplying it by the volume, right? Now the volume is over here, right? So that would be my volume, and then the density is just water. So once I have all of this, okay, then my buoyant force is going to be the density multiplied by the volume, okay, and multiplied by gravity, which is just simply 9.8. Okay, so let's try to see what this would equal. So I'm going to just take out my calculator. So here, 0.12 multiplied by 0.18 multiplied by 0.3. So it's going to be a very small number. That's my volume. My density in this case is 1,000, because you know what? I'm going to actually write all of this out because I think I need it for the other example. So so I don't have to keep doing it over and over. So this would be in meters cubed. Okay, so I'm going to keep that volume. So now times 1,000. And then finally times 9.8, so this would have been 63.504 newtons, right? Now rounded to maybe two significant figures was just 64 newtons, okay, and that's the buoyant force. So you would have been feeling this force, okay, this is the upward force, okay, as you would be submerging something down into the water, all right? So that's the part A component. Part B, what would be the buoyant force if you submerged it in mercury? All right, well, so it's good that I actually kept it. I had a feeling that we're going to need it. So what this would mean is, the buoyant force, I don't have to re-explain this concept. So this is exactly the same, except our density changes. So if I go back in here, so I'm going to remove the density of water. Let's put the density of the mercury, which is quite a lot bigger, and substitute it in. And look at this. So the 8 and I'll just keep it 6, 3, 6, 5, 4, 4 newtons, or 8, 60 newtons. Again, this is upwards, in terms of the force. It's quite a lot more than the water itself. And of course, mercury is super dense, so we're going to be feeling quite a lot of force pushing us upwards, trying to prevent this thing, if we want to be able to submerge it, in mercury. Now, for part C, it says repeat A and B if the object is submerged, but now 25 meters below the surface. All right. So this is, interesting because, so if I'm going to kind of go back in here, so here it says, we've submerged it, but we submerged it fully. So for parts A and for parts B. So that would have been taking this entire object and then submerging it fully in water, right? And then taking it and submerging it fully in mercury. So now it says, repeat parts A and B if we submerge it to 25 meters below the surface. Does that make a difference, right? And the answer is no, It will not make a difference, because when you're submerging it, if you fully submerge something, so it doesn't matter if it's just kind of below the surface, or if it's, further down the surface, you have kind of two forces, right? You have the force which is below the object, pushing this upwards. So you would have had, a force which is pushing this upwards, and then you also have pressure which is down, right? So you have pressure up and pressure down. So what would happen is all these forces, and that would be the buoyant force which is winning out, this would be bigger, than this one which is pressing it down. And that's just basically because you have displaced, right? So this is a little bit deeper in. So this is a good question to be able to ask, because you might think like, oh, I have to do more calculations. And the answer is no. You still displace the same amount of fluid because your box, doesn't change. Now we're assuming, it doesn't get compressed in any way, or it doesn't get broken or something like that. So in that case, if we have something of an object which is in this size, it's going to be exactly, so the answers would be the same for part C, as we did for part A and part B. All right, so that is it, for this example. Here's our last example, at least for this video. So we have a spherical medical device, and it has been submerged in water. All right, so in terms of water, so we know what this density is. Water is 1,000 kilograms per meter cubed. So we'll assume that if it's not given. It has been found that the buoyant force present on the object is 2,500 newtons. So now, the buoyant force is always equivalent to the weight that would have been displaced by the object itself, right? So that's what it's going to be, which is mass times gravity, or in other words, so this is for mass. This comes from density, that mass is equal to density times the volume that it occupies. So that just comes from density equals mass over volume. So really, this is just this equation right here. So that's the buoyant force for any object, that we have. All right, now we know what the buoyant force is. It's 2,500 newtons. That's the buoyant force. What was the volume of the medical device? So if we wanted to know what the volume is, well, the density we have, so it's water. We have that it's 9.8, that's gravity, and then this is the volume. So I can certainly solve this for volume. So that wouldn't be that big of an issue in here. Turns out everything is in metric standard units, so this makes it a little bit simpler. So we have that. So 2,500, and then divided by 1,000 times 9.8. Okay, so that's the volume. So it's actually a pretty big volume, okay, in there, etc., because it's in meters cubed. All right. What was the radius? Now, if you're rounding this, okay, so you can certainly round this. I just took a peek. Okay, it looks like it's two significant figures. You can do that. Now, for part B, what was the radius of the sphere for this device? Okay, well, so that means, we kind of have to recall what the volume of a sphere is. So volume of a sphere, so it's just 4, okay, over 3, and pi, and this, I guess this is r cubed. Okay, so we have the volume. And now that we have that, well, we can substitute this in. So this is my volume, all right? So 0.255, okay, etc. And now we're going to have to solve for this r cubed. So now be careful, because you're going to have to solve this formula. So this is going to be times. So notice we're going to be multiplying both sides by 3 to get rid of the 3. Okay, we're going to be dividing both sides by 4 to get rid of the 4. So dividing both sides by 4. We're going to be dividing both sides by pi, okay, to get rid of the pi. So that's going to be that. That's going to give us r cubed. Okay, so let's see what that gives us. Answer times 3 and divided by, this is going to be divided by 4 pi equals. All right, so that's what we have there. So 0.0609, etc. Okay. And now we're going to take our answer and we're going to take the cubed root of this. All right, so the easiest thing to do for me now is just to do, okay, this is, okay, if you remember, okay, and if you're familiar, okay, with this, so you would have to take this, okay, and get rid of it by taking the cubed root, okay, of both sides. Okay, so that's what we would do. And now an easy way to do that is actually to take it to the exponent of 1 over 3, okay, which is equivalent. So if you take, okay, this of x, it equals the same thing as x to the 1 over 3. And this is a fact of fractional exponents. I'll put up a link up above there, okay, if you want to see that math component, okay, for this. So I'm going to do that in here. And here's our answer. So r is equal to 0.3934, etc. So the two significant figures. So about 39 centimeters. All right, so that's what we would have had for this example. And that finishes off, okay, so this set of questions. Thanks for watching. We'll see you in a future video. Bye, everybody.